Welcome back, everyone. Our next speaker is Professor Chen from Yale Mathematics Sciences Center of Tsinghua University. His research interests mainly focus on elliptic PDEs and their cross applications with integral systems and number theory. He also has done a lot of distinguished work on these topics. The title of his talk is Mean Field Equations on Torus, Pre-modular Forms, and Painleve VI equation. Let's welcome Professor Chen.
Thanks very much for the invitation and the introduction. So today I will talk about mean field equation on torus. It is an elliptic equation, and I want to introduce its connection with pre-modular force from number theory and Painleve VI equation from any global system. So this talk is mainly based on joint papers with Professor Chang Shoulin from Taiwan University. So let's consider singular Liouville equation. So we consider the flat torus generated by the vector 1 and tau. So this tau is a flat torus in the plane. So let's consider the singular Liouville equation. The left-hand side is the Laplacian plus EU, and the right-hand side there are some Dirac measures on the half period of the torus. Omega 0 is 0, and omega 1 tau 1 plus tau. These three are the basic periods of the torus. So omega k over 2 is a half period, and here are some coefficients a pi times some integer in k. So this problem is equivalent to a doubly periodic problem on a parallelogram. So because on the torus, z plus 1, z and z plus tau are the same point. So we starting from this simple looking elliptic. So this equation arises from the prescribing curvature problem from conformal geometry. The solution U will lead to a new metric G on the flat torus with a constant curvature positive one, but has some conical singularity at this point because the equation right hand side has some Dirac measure on the right hand side. So it also belongs to a more general family of the so-called mean field equation on any compact Riemann surface. And here are very Dirac measures, and this equation arises from the statistical physics, so called mean field equation. This equation can be written in this form. So it is a special case of this general mean field equation. So our motivation comes from this more simple looking equation. The right hand side now is a single Dirac measure and with a positive parameter rho. So if rho is not a pi times some integer, then from these two papers they already proved this equation always has solutions. So the remaining case is rho is a pi times some integer n. But this case tends to be very challenging. And it turns out whether this equation have solutions or not depends essentially on the geometry of the torus. That is, depends on the choice of the second vector tau. This phenomenon was first studied by Chang Shoulin and Jinlong Wang. So in this paper, they studied the first case. The right hand side is just a pi. They proved that if tau is purely imaginary, that is the torus is a rectangular torus, then this equation have no solution. But if the real part of tau is 1/2, so that is the torus is lambda torus, then that is this two constant b0 and b1. such that when the imaginary part of tau b smaller than b0 or bigger than b1, then this equation has solution. And if b between b0 and b1, then this equation have no solution. Have no solution. So for this equation, whether the solution exists or not depends on the choice of the tau. Several years ago, Professor Lin and me proved generalized this result. Generalize this result to general a pi times integer n. That is, we prove that when tau is purely imaginary, then this equation, the right hand side is a pi times integer n. For any n, this equation have no solution. Have no solution. So remember, we already introduced that if this law is not a pi times, then this equation always has solution. So these two results together told us when the torus is a rectangular torus, then this equation has solution if and only if rho is not a multiple of a pi. This is an if and only if. So no, the orange, the usual Laplace. Yeah, is the usual. So, okay. So this fact told us when this parameter is perturbative has some epsilon, then this equation does have solutions. So this is one the first difficulty. Another difficulty is if you perturbate the tau, then this equation may also have solutions. May also have solutions. So these two difficulties makes this non-existent result hard to prove by PDE methods. So we prove this theory by the spectral theory of the Lamarck pattern from any global system. And so far, we cannot find a PDE proof. So now a natural question is: so since solution is this or not depends on the choice of tau, so can we give a precise description of such tau, that tau? So one way is to use the green function. Another way is to use the pre-modular form. So let's first look at the green function. So let's consider the green function on the first torus. It's defined by this equation. So this green function means the singularity is fixed at the origin. So then this green function is an even function. So we define a gn with n variable defined by this green function g. So Z is called a critical point, means the derivative with respect to Zi for every I is equal to 0. So since G is even, so we know that if this is a critical point, then this is also a critical point. But these two critical points may be the same in the torus. So if they are the same, we call it a trivial critical point. So if they are different, then we call the non-trivial critical point. So non-trivial critical point, if it exists, must be impaired. So I will consider the the critical point of this Gn. So let's consider the blow-up phenomenon of this equation. So let rho equal rho k tends to a pi n, and the uk be a solution. Assume that this sequence of solution blow up. Then if rho k is not a pi n for large k, then this uk will have n blow-up points, and the n blow-up points will give a trivial critical point of this Gm. If rho k is always a pi n, then the blow-up point set also contains n points, but it will give a non-trivial critical point of this Gn. Now, furthermore, this theory is proved by Professor Jingli Zhai, Chang Shoulin, and Wang Jinlong. And furthermore, then this equation have solutions if and only if the corresponding Gn on this torus has non-trivial point. So this result give a description of the torus when this equation has solutions. The if the torus is for this torus the corresponding Gn has non-trivial point, then this equation will have solutions. So from this theory, you can see both trivial and non-trivial critical points are important for the bubbling phenomenon of this equation. So a large open problem is how many critical points might this function have. So Professor Lin and me, we solved this question for rectangular torus. So we let tau is purely imaginary. Then we can prove this Gn has exactly 2m plus 1 critical points. And all are trivial critical points. And furthermore, they are all non-degenerate. So that the non-degeneracy of critical points is important when we consider when in the constructing bubbly solutions with the reduction approach, and also important in the proof of the local uniqueness. So here we'll give an example that our previous theory can be applied to count the exact number of solutions. So still consider purely imaginary tau, that is E tau is a flat rectangular torus. Then given integer n, we can prove if rho is a pi times, then this equation have no solution. This result we already introduced before. But if rho times a pi is between this small neighborhood, then the solution number is n. And if rho times n pi is between this interval, then the solution number is m plus 1. So this gives a very beautiful example that the solution number depends very easy on the parameter rho. When this is a little smaller than n, the solution number is n. Equal n is 0, and big than slightly bigger than n, then the solution number is n plus 1. But if the torus is not rectangular torus, then this result should be false. So this is from the viewpoint of Green functions. So now let's turn to the pre-module 4. So we record the Weierstrass elliptic function. This P function defined in this way. It will know that it satisfies this cubic equation, and we also consider the Weierstrass zeta function. It is a primitive function of P, but up to a set. And this zeta function is R-monomorphic and has 2 Poisson periods because its derivative is double periodic. So zeta is not double. If you consider plus a period, then that is a constant. It's a constant eta k. So now we give given two parameter r and s, we define zrs as a function of tau using this zeta function and 2 Poisson periods eta 1 and eta 2. If rs are both half integers or integers, then this function is trivial. So we don't consider rs half periods. So this function was first introduced 100 years ago by Aiken, and she proved that if Rs belong to this Qn for some n, then this Rs is a modular 4 with respect to this group gamma n. let's recall the definition of modular form. A holomorphic function defined on the alpha plane H F is called a modular form of weight K with respect to some subgroup G if we consider the fractional transformation of tau by a metric ABCD, then have this transformation. So, for example, in the cubic equation of the P function, here are G2, G3, and E1, E2, E3. So here are 5 classical special functions. So these 5 special functions are all well-known modular forms. So for this ZRS tau, when RS belong to Qn, then it satisfies this formula. So it is a modular form of weight 1 with respect to gamma n. So that is for general RS, this RS tau is not a modular form. But when RS are both rational functions, rational numbers, then this ZRS tau is a modular form. So due to this reason, we call this ZRS tau is a pre-modular form. So Professor Lin and Wang, they proved that that is a pre-modular form. We call it ZNRS. It is a polynomial of this ZRS and this pay prime G2, G3 with rational coefficients of this weight such that this equation have solutions if and only if tau is a zero of this pre-modular form. So this is another description of the torus or the tau from the viewpoint of zeros of pre-modular form, such that this equation have solutions. So this theory is proved by the method of algebraic geometry. So we want to generalize this result to the 4 singular sources case. With the right hand side, now we have 4 singular sources. This equation has only a singular source. But for this problem, it turns out that we cannot give a description from the viewpoint of critical point of the multiple Green function. So we try to study it from the pre-modular form. So joined with Professor Lin and Ting Longguo both from Taiwan, we also proved that for general n, that also exists a pre-modular form such that this equation have even solutions if and only if tau is a zero of such pre-modular form. The basic procedure of our proof is also to apply the method of algebraic geometry. But the main novelty of proof is how to determine the weight of this pre-modular form. The method cannot deal with for the 4 singular source case, and we use another method to determine this number. So here are some examples. Here are some examples of the explicit expression of such pre-modular forms. Where it looks very complicated when the n is large. Here's also some new examples. So in general, this pre-modular form, for general case, you cannot to expect to write down the expression of such pre-modular form. But this pre-modular form is probably important when we apply to the when we apply to study the curvature equation or the mean field equation. So we want to study some properties of this pre-modular form. So joined with Professor Lin, first we can prove that this pre-modular function of tau always has at most a simple zero. Any zero are simple. Any zero are simple. So this result is not trivial due to at least two reasons. One is that the expression is not known for general n. Another reason is even for these cases, the expression is known, but the derivative with respect to tau is very complicated. Very complicated. So we prove this theory by studying the deep connection between the pre-modular 4 and the Painleve VI equation that I will introduce later. Painleve VI equation is an important nonlinear ODE in the global system. So let's come back to this this PDE. If let U is an even solution, then you can, and Z we consider complex variable, then you consider this function UZZ minus 1 over 2 U this word. You consider its derivative with Z bar. Using this equation, you know is 0. So this function is a Melomorph function. Melomorph function. And using the local behavior, because the right hand side has some direct measure, using the local behavior of the solution, you know that this Melomorph function has double poles at each singularity. So the conclusion is since U is a function on the torus, so U is double periodic. So the conclusion is this equation, this function is an even elliptic function, and with double pole as the half period. So the real theory told us that is a constant B such that this function can be written down by the Weierstrass P function. So we consider this is a potential function. We consider this part is a potential function and consider the corresponding second order linear ODE. Linear ODE we consider complex variable. Then from here you know that E minus 1 over 2 UZ is a solution of this ODE. So there will be a basis of solution y1, y2 such that this function can be expressed as in this way, because this one is positive and is positive, positive. So this second order linear ODE also studied more than 1 century ago, and it is known as the elliptic form of the well-known Henon equation. Henon equation is the second order function differential equation with 4 regular singular points. It is an important linear ODE in global system, and this equation is the elliptic form of this Henon equation. So for this Henon equation, remember we consider complex variable. So since this potential has singularities at the half periods, so this equation have 4 regular singular points. But it's easy to prove that any solution is single valued near such singularity. So after analytic continuation, any solution is metamorphic in the complex space. So let's consider the two base periods. If y1, y2 are a solution, then y1 z plus omega j, this is also a solution. So that will be a monotomy matrix. We call it nj, such that this formula holds. Then n1 and n2 are commute. So we are interested in when n1 n2 can be diagonalized simultaneously. So there will be a so-called spectral polynomial of B. So where is B? B is here. So that is a polynomial of B such that If B is not a zero of this polynomial, then N1 and N2 can be diagnosed simultaneously. So we written in this way, And so there are two important parameters, R and S. We call it DRS known as the monodromy data of this complex linear ODE. If these R's are real, then there is a base Y1 basis of solutions Y1 and Y2 such that these quantities are both double periodic, because when Rs are real, then the absolute value of these eigenvalues are both one. So from here we can construct a solution of the EDPDE using from this ODE. So we are interested in the monodromy data R and S. So we got a map phi n from the tau and B. Remember, given tau and B, such that B is not a zero of the polynomial, then we got the monodromy data R and S. The monodromy data R and S. So we got a map. From tau and B to the monodromy data R and S. So we proved so this first we give a description of the monodromy data R and S. So given R and S, we prove that exists B and a fixed tau zero. That exists B such that this RS is a monodromy data of this. Oh, sorry, this is tau zero. Such that this RS is a monodromy data of this from here, if and only if this tau zero is a zero of the pre-modular form. This theory was first proved in several years ago, and the additional assumptions that the R plus S tau zero is not the lattice point of the torus. When R plus S tau zero is the lattice point, then this function and also the pay function, pay prime are also infinity. This is the main difficulty at that time. So this theory we delete this additional assumption. And we study the property of this map phi n, and it turns out this very complicated map satisfies a very surprising universal law. We prove that this phi n is holomorphic and locally one-to-one and satisfies this identity. For any n and any tau b. So first, the constant is independent of tau b, and second, this constant is universal. A pi square independent of n. But so far we cannot find a geometric expression of this universal. But we already find some application of this universal law. For example, we use this universal law to study the spectrum of the associated second order linear Schrödinger operator. So how to prove this universal law? Again, we need to apply the pre-modular form and the Painleve VI equation. So for the simplest case, for this simple case, that this universal law can be proved by a direct computation. And for the second case, it also proved by direct computation, although the computation is already very complicated. But for all the other cases, we prove this universal law by an induction approach, where we need to use the Painleve VI equation. So let's then to introduce the Painleve VI equation. let's consider a very simple nonlinear ODE. This very simple nonlinear ODE. Easy to see that for given any complex parameter C T times C 1/2 is the solution of this nonlinear ODE. So from here you know that this solution YC is a multi-valued with a branch point C, and this branch point C cannot be determined from this equation, and it depends on the choice of the initial depth. So such kind of branch points are called movable branch points. So an ODE is called to satisfy the Painleve property if it has no movable branch points. So one important problem of analysis in the 19th century is find all the ODEs of this form which satisfy the Painleve property. Here, capital F is a polynomial in every variable. So Painleve equation are 6 nonlinear ODEs satisfying the Painleve property that were discovered by Painleve and his work in early this time. So the Painleve equation was first discovered for mathematical reasons, but it turns out the Painleve equations appeared in many physical problems. So Painleve equation becomes very important in the field of integrable systems. So the Painleve VI equation is a second order nonlinear ODE in this form. It has 4 free parameters alpha, beta, gamma, and delta. So this ODE looks very complicated, but its solution has a Painleve property. That is, any solution has a branch point at most at 0, 1, infinity. For any other for any other point not 0, 1, infinity, solution is metamorphic at those points. So it is natural to lift this equation to the universal covering space, the capital H of this space by the following transformation. This is the P function. This EK tau is the P function, the value of the P function of the half periods. So under this transformation, this function will be single valued. So this equation of lambda t looks very complicated. But under this transformation, then the function, the equation for p looks very easy. So lambda t is the solution of the Painleve VI equation if and only if this p tau is here. P tau satisfies this equation. We call it the elliptic form of Painleve VI equation. So to connect with the previous pre-modular form, we consider the alpha, beta, gamma, delta in terms of nk in this way, and all equivalent is the elliptic Painleve VI equation with parameters with alpha k in terms of nk in this way. So in 1995, Zhijie proved the following beautiful formula. He proved that given any RS, we define PRS 0 tau by this formula. Then this PRS tau 0 is a solution of the elliptic Painleve VI equation with parameter 0. So the important thing is the denominator of this formula is this function ZRS tau. ZRS tau we defined before. This pre-modular form. So this is for nk or 0. For general nk, it is known that solution can be obtained from this one using the well-known Okamoto transformation. So we denote by PRSN to the solution obtained from the PRS0 with Okamoto transformation. For example, if n is 1, 0, 0, 0, then the formula in this way. So this formula is already a little complicated than this one. But the important thing is the denominator term is this. This is the second pre-modular form we introduced here. This one. So this pre-modular form also appeared in the expression of solution of Painleve VI equation. But for general NK, and we cannot write down especially the expression of the solution of Painleve. But we can prove that for example, this formula tells us that if this one equals 0, then the left hand side equal infinity. So this means that in this one will be 0. Also, if this one equals 0, then the left hand side is infinity. So this denominator also 0. So for general n, we can prove that although we cannot write down the expression of this function, but we can prove that PRSN tau 0 equals 0 if and only if tau 0 is either a 0 of this ZRS n plus. N plus is n0 plus 1, or a 0 of n minus 0 or minus 1. So this results suggests that both these two pre-modular forms should appear in the denominator of the expression of the solution of the Painleve VI equation. But this problem seems very difficult. Still remains open. But from here we can give the proof of the universal law. Now we can see the solution of Painleve VI equation and take derivative with respect to the two parameters r and s, call it y1 and y2, and then these two functions solve the linearized equation of the elliptic Painleve VI equation. So since this second order equation has no the y1 term, so the Wronski of these two equations, these two functions is a constant, independent of tau, but will morphic in an R and S. So the key proof in our the key step in our proof is to prove the following three statements is equivalent. That is, the Wronski is also independent of R and S. The Wronski is always -1. It is equivalent to for n minus the universal law holds, and also equivalent to n plus for n plus the universal law holds. So this means 2 and 3 are equivalent. So we already compute for these two cases the universal law holds. So by this lemma, 2 and 3 are equivalent. So from here you know that. Then this means 3, 0, 0 the universal host. And this means for 0, 0, this universal host. So by induction argument, we can prove for any n the universal host. So this is our basic idea of the proof. So we need, the key step is to establish the precise connection between the pre-modular 4 and the Painleve VI equation. Painleve VI equation. So I'll stop here. Thank you very much.
Thank you, Professor Chen. Any questions?
We don't consider hygiene case because we only consider the case of the flat torus. So for this case, we can use some tools from complex analysis, in particular the theory of elliptic functions. Yes. So our method is relies essentially on the elliptic functions. Yes.
Any questions?
New multiple we also consider, but we cannot obtain result of this type. We can obtain some rough result, but not results like this very very delicate. Yes. More point we also, for example, if for multiple points, we can establish some connection with the theory of the stationary KdV hierarchy. For general, for equation like this, or for this equation, we can establish some connection between this equation with the stationary hierarchy, because for this it will have some connection with this function. This function is no when pk satisfies some conditions, this function will be solution of the stationary KdV hierarchy. So by using this function, we can establish some connection between this equation and the theory of stationary KdV hierarchy.
Okay. Any questions? If there's no question, let's end here. Thank you, Professor.
Thank you.